Hello all, welcome to Module 2 Part 1 of C80201 Mechanics of Solids. So in this lecture we will be discussing about temperature stresses. Okay, so first topic is temperature stresses on a single bar. So which can be occur on rod, rails, etc. So first question which is on a rod, and question is that a rod 2 meter long at a temperature at 10 degrees Celsius. Find the expansion of rod when the temperature is raised to 80 degrees Celsius and if this expansion is prevented. Find the stresses induced in the material of the rod where E is equal to 1 into 10 raised to 5 megapascal and alpha equal to 0.00012 per degree Celsius. So let's analyze the question. Here you have provided a rod which is having a length of 2 meter and which is at a temperature of 10 degrees Celsius. So that is the initial temperature. Then you can see the temperature is raised to 80 degrees Celsius. That means the change in temperature will be 80 minus 10 degrees Celsius. Okay, that means delta T will be 80 minus 10. Then the clause is that if the expansion is prevented, so that the stress will induce in the rod. Find the stress induced in the material of the rod if Young's modulus is equal to 1 into 10 raised to 5 megapascal, which is also Newton per mm square, and coefficient of thermal expansion, that is alpha, equal to 0.00012 per degree Celsius. So first of all, write down the given data, that is L equal to 2 meter, T1 equal to 10 degrees Celsius, T2 equal to 80 degrees Celsius, and Young's modulus E equal to 1 into 10 raised to 5 Newton per mm square. Then we have to find out the value of thermal stress or temperature stress induced in the rod, and the equation is alpha delta T into E. Okay, so before that we have to find out the expansion of rod. Expansion means delta L. How will you find out? Use the equation alpha L delta T, or delta T is the change in temperature, so that alpha into L into T2 minus T1. All the data are given in the question. Just substitute and find out the answer. You will get it as 1.68 mm. Now thermal stress, which is equal to alpha delta T into E, where alpha, which is given in the question, delta T we already know, and E, which is also given in the question, so that which is equal to 84 into 10 raised to 6 Newton per mm square. Here in the question it is given that the expansion is prevented, so that we know the stress will be induced in the material of the rod, and the equation for stress, which is alpha delta T into E. Okay, so let's move on to the next problem. A steel rod 3 cm diameter, 5 meter long, is connected to two grips and the rod is maintained at a temperature at 95 degrees Celsius. Determine the stress and pull exerted when the temperature falls to 30 degrees Celsius. Okay, so the question is regarding a rod which is having a diameter of 3 cm and length of 5 meter, and which is connected at two grips and which is maintained at a temperature of 95 degrees Celsius. So we have to find out the values of stress and pull when the temperature falls to 30 degrees Celsius. So as the temperature decreases, there will be some contraction occurs, and we have to find out the values of that much stress and pull exerted on the steel rod, provided with two conditions, that is when the ends does not yield, and second one is when the ends yield by 0.12 centimeter. So when the ends does not yield, we doesn't need to consider that yielding. So we can consider the total contraction by taking the temperature reduction. Okay, so it is given in the question that Young's modulus E is equal to 2 into 10 raised to 5 megapascal, which is also equal to 2 into 10 raised to 5 Newton per mm square, and coefficient of thermal expansion alpha equal to 12 into 10 raised to minus 6 per degree Celsius. Okay, now when the ends does not yield, the stress developed, which is equal to alpha delta T into E. Okay, So that's equal to alpha into delta T is the change in temperature, that into E. So you will get the answer as 156 Newton per mm square. Now what about the pull? Just multiply the stress into area. That is 156 into pi by 4 d square, and that's equal to 110,269.90 Newton. Okay. Now stress when the ends yield by 0.12 centimeter. So we have to consider this much yield from the contraction. So what about the contraction, which is alpha L delta T? So that's a expansion or contraction when the temperature rises or falls. So that much value of yielding should be subtracted from this contraction. So alpha L delta T minus small delta divided by L into E. So that's equal to alpha into L into delta T minus small delta is the amount of yield. That divided by L into E will give the value of stress, and that's equal to 108 Newton per mm square. Now the pull P is equal to stress into area, that is 108 into pi by 4 into 30 square, that's equal to 76302 Newton. Okay. So let's move on to the next problem. A railway line is laid so that there is no stress in the rails at 8 degrees Celsius. Calculate the stress on the rails at 50 degrees Celsius if there is no allowance for expansion. The stress in the rails if there is an expansion allowance of 8 mm. The expansion allowance if the stress in the rails is to be 0. The maximum temperature to have no stress in the rails if the expansion allowance is 12 mm. The rails are 30 meter long. Take alpha equal to 12 into 10 raised to minus 6 per degree Celsius, and coefficient of thermal, that is coefficient of thermal expansion, and Young's modulus E equal to 2 into 10 raised to 5 Newton per mm square. So it is a KTU question paper question. So the question is regarding a railway line, and which is initially at a temperature of 8 degrees Celsius. Now the temperature is increases up to 50 degrees Celsius, and if there is no allowance for expansion is there. So if there is no allowance for expansion on the railway, there will be stress induced in the rail. Okay. So what is the equation for free expansion? That is alpha delta T into L. So that the value of strain will be alpha into delta T. That is, what do you mean by strain? Change in dimension divided by original dimension. So that strain will be alpha into delta T. Now we have to find out the value of stress. If we know the value of strain, just multiply strain into Young's modulus. So that alpha into delta T into E will be the stress induced in the rail. Okay. Now, what is alpha, which is the coefficient of thermal expansion? What is delta T, which is the change in temperature? So, initially the rail was at a temperature of 8 degrees Celsius, and which is increased to 50 degrees Celsius. So, that the change in temperature will be 50 minus 8. That into Young's modulus, that is 2 into 10 raised to 5. So that the stress induced, which is equal to 100.8 Newton per mm square. Okay. Now the second question, the stress if there is an expansion allowance of 8 mm. So here it is provided with an allowance of 8 mm. So actually we have the value of free expansion, that is by alpha delta T into L, but there is an allowance for expansion is provided, so that we have to consider that from that total expansion. Okay. So the total expansion will be alpha delta T into L, that minus expansion allowance that we have to consider. For that, just subtract alpha delta T into L minus small delta. Okay. Where small delta is the value of expansion allowance. So that's equal to alpha delta T into L minus delta into Young's modulus value. Okay. That divided by original length of the rail, so that the answer will be 47.46 Newton per mm square. Okay, so this is the equation for expansion, that is alpha delta T L minus small delta, that divided by L will give the value strain. That into Young's modulus will give the value of stress induced. Okay. Now, the expansion elements for zero stress in the rails. Now, the question is to find out the value of small delta, and which is given that zero stress. That means the equation stress which is equal to 0. So that alpha delta T into L minus small delta divided by L into E, which is equal to 0. And as we all know, Young's modulus cannot be equal to 0, and also the length of the rails cannot be equal to 0. So the remaining part, that is alpha delta T into L minus small delta, which is equal to 0. From that, small delta which is equal to 15.12 mm. So which is the expansion produced in the rails with a zero stress in the rails. Okay. Now the next question, we have to find out the value of temperature for zero stress if expansion allowance is 12 mm. In the third case, we found out the value of expansion allowance. So in this case, the expansion allowance is given in the question, and instead of expansion allowance, we have to find out the value of temperature. Okay, so for zero stress, we know the equation, that is delta equal to alpha delta T into L, and here delta which is given as 12 mm, that is alpha delta T into L is equal to 12 mm, so that the temperature which is equal to delta divided by alpha L, and that's equal to 33.33 degrees Celsius. Okay. The next topic is temperature stress on a composite bar. So till now we were discussing about the temperature stresses on railway, rail, road, etc. Now we are discussing the temperature stress on a composite bar. So we already know what is a composite bar, which is a bar consisting of two different materials. Okay, so one which can be aligned inside another material, or which can be arranged parallel manner. Okay, so the temperature stress on a composite bar. Let's discuss the first problem. A steel rod which is 20 mm diameter passes centrally through a copper tube of 50 mm external diameter and 40 mm internal diameter. 50 mm external diameter and 40 mm internal diameter. The tube is closed at the ends by rigid plates of negligible thickness. If the temperature of the composite bar is reached by 50 degrees Celsius, calculate the stresses developed in copper and steel. So take Young's modulus for steel, which is equal to 200 giganewton per meter square, and that for copper is equal to 100 giganewton per meter square, and also alpha S value and alpha C value, which is given in the question. Okay, so let's find out the solution. So first of all, let's write down the given data for steel rod and also copper rod. Okay, so first of all, steel rod, regarding the length which is not given in the question, so let's take the length as L mm. Okay, now the temperature change, that is delta T. Here it is given in the question that the temperature is raised by 50, so that delta T equal to 50 degrees Celsius. Okay, now the diameter which is given as 20 mm, a steel rod which is a solid section and which is having a diameter of 20 mm. Now what about the area of steel rod, which is equal to pi by 4 into d square, and that's equal to 314.159 mm square. Now the Young's modulus value for steel, which is equal to 200 into 10 raised to 9, that is giganewton to Newton conversion, into 10 raised to minus 6. So that much Newton per mm square will be the Young's modulus value for steel. Now the coefficient of thermal expansion value for steel, which is equal to 12 into 10 raised to minus 6 per degree Celsius. Let's write down the data of copper tube, that is the inner diameter which is 40 mm, the external diameter which is 50 mm. If a material is having inner and external diameter, so we have to find out the area, that is pi by 4 divided by capital D square minus small d square, and which is obtained as 706.858 mm square. Now the Young's modulus value for copper tube, which is 100 giganewton per meter square, and that's equal to 100 into 10 raised to 9 into 10 raised to minus 6 Newton per mm square. Okay, now the coefficient of thermal expansion for copper tube, and that's equal to 18 into 10 raised to minus 6 per degree Celsius. So for solving the temperature stress on composite bar, the first equation is the tensile force or the compressive force produced on the both bar will be equal. That is sigma S into AS, which is equal to sigma C into AC. That is sigma S divided by sigma C is equal to AC divided by AS. So we can establish a relationship between sigma S and sigma C. That is sigma S is equal to 2.25 into sigma C. Okay. Now, so we have to find out the actual expansion for copper and steel individually. Okay, so what do you mean by the actual expansion of copper, which is the alpha delta T into L value, that minus the expansion, natural expansion. So due to the force. Okay, so this value is alpha delta T into L, that is temperature expansion, that minus the expansion due to the force. Okay, so that is 18 into 10 raised to minus 6, that is alpha into delta T into L minus, we know the equation delta L equal to PL by AE. In terms of stress, we can write it as sigma C into L divided by E. Okay, and that's equal to 9 into 10 raised to minus 4 into L minus 1 into 10 raised to minus 5 into sigma C into L. So simplify that equation. Okay, so why this minus sign appears here? We know the coefficient of thermal expansion is more than it is more for copper than steel. So there will be a compressive stress induced. So that for making that, we have to put a negative sign, or we have to subtract the value of expansion minus the expansion due to the applied load. Okay, so the actual expansion for steel, here we have a additive symbol, that is plus. So this is the expansion due to temperature change, and that plus expansion due to load applied, that is alpha S L into delta T plus sigma S into L divided by EC. So simplify the equation in terms of L and sigma C into L. That means we have to apply the value of sigma S is equal to 2.25 sigma C here, and simplify the equation. And we know the actual expansion of copper, which is equal to actual expansion of steel, since it is a composite bar. So just equate the two equations and solve for sigma C. So you will obtain sigma C as 14.117 Newton per mm square, and we know sigma S is equal to 2.25 sigma C, and from that sigma C, which is equal to 31.763 Newton per mm square. Okay. Now this is a special case problem, that is thermal stress with fixed support. Okay, so let's directly move on to a problem. A composite bar made up of aluminum and steel is held between two supports as shown in figure. The bars are stress free at a temperature of 38 degrees Celsius. What will be the stress in the two sections when the temperature is 21 degrees Celsius? First case, if the supports are unyielding. Second case, if the supports come nearer to each other by 0.1 mm. It can be assumed that the change of temperature is uniform all along the length of the bar. Take ES equal to 210 GPa and EA equal to 74 GPa. Alpha S is equal to 11.7 into 10 raised to minus 6 per degree Celsius, and alpha A equal to 23.4 into 10 raised to minus 6 per degree Celsius. Okay, so in this case, as you can see, both the ends of the bars are fixed. That means if the expansion is prevented, so that the stress will be induced on the both bars, that is steel and aluminium. Okay, so we have to find out the values of that stress in two cases, that is when the supports are unyielding and when the supports are come nearer to each other by 0.1 mm. Okay, so the two materials, steel which is 50 mm dia and aluminum which is 25 mm dia, and the length of the steel which is 0.6 mm and the length of aluminum bar which is 0.3 meter. Okay, now the length of the steel section which is given as 600 mm, length of aluminum section which is 300 mm. Now the area of cross section of steel section, since it is a since the diameter is given in the question, we can find out the area of steel section by using pi by 4 d square. Now the area of cross section of aluminum section which is pi by 4 into 25 square, and the modulus of elasticity values are given. Okay, and also the coefficient of thermal expansion values are given. Now the change in temperature we can find out by subtracting from final minus initial, and that's equal to minus 17 degrees Celsius. So we can take the value as 17 degree Celsius. Okay, now if P be the pull from the end support and sigma S and sigma be the stresses in the steel and aluminum section, so we can establish the relationship between sigma S and sigma A by the usual equation, that is load will be equal, that is sigma S divided by sigma A is equal to AA divided by AS. That means sigma S into AS is equal to sigma A into AA, and from that sigma S divided by sigma A equal to AA divided by AS, and from that sigma S is equal to 0.25 sigma A. Now we have two cases, that is if the supports are unyielding. Okay, in that case, if the supports are unyielding, that means the free contraction due to temperature change will be is equal to expansion due to tensile pull from the supports. Okay, that means here you can see which is alpha delta T into L for steel, and here also you can see it is alpha delta T into L for aluminum. That is the total expansion due to temperature change will be equal to the expansion due to tensile pull from the support. That is the equation, that is the total expansion or contraction due to temperature change will be equal to the total expansion due to pull from the supports. Here the temperature is decreases, so that the contraction will be developed. Okay, so just apply the values for alpha delta T into L plus alpha A delta T into LA, that's equal to sigma S ES into LS plus sigma A divided by EA into LA. Okay, so apply the value as sigma S is equal to 0.25 sigma A here. Okay, and from this find out the value of sigma A. Now sigma A equal to 50.055 Newton per mm square, and sigma S is equal to 0.25 into 50.055, that's equal to 12.51 Newton per mm square. So the tensile stress which is developed in the steel section is equal to 12.51 Newton per mm square, and the tensile stress in aluminum section which is equal to 50.05 Newton per mm square. Okay, now the next case, if the supports come nearer by 0.1 mm, that means here a small delta, that is allowable expansion or allowable contraction is given in the question. So we have to consider this value from the total contraction value. Okay, that means find out the value of total contraction and find out and subtract this delta from that total contraction and again equate. Okay, so you will get the value of sigma A as 29.08 Newton per mm square and sigma S as 0.25 sigma A, that is 7.27. So there is two cases given in the question, and one which is if there is no yielding, or the second case if the supports come nearer by 0.1 mm. Okay, in the first case we equated the total contraction to the expansion or contraction due to pull, that means the expansion due to pull. In the second case we have to consider this yielding of the support, that is by 0.1 mm. Okay,
So the final answer for the tensile stress in steel section, which is 7.27 Newton per mm square, and the tensile stress in aluminium section, which is 29.08 Newton per mm square. Okay.
I hope all the problems are clear for all of you. So thank you all. Bye. See you with the second part. Okay. Thank you.